NAUMOV. Panche, I see you. That's great. Maybe now you can still. Oh, thank you for the underground. What you put underground. Okay, so a small biography. So Panche is actually at the New York University Abu Dhabi, with cross appointment with New York University, New York. He performed his PhD in materials chemistry. In chemistry and material science, sorry, in Tokyo in 2004, and he continued in Osaka and Kyoto in Japan. After he was recipient in 2018, recipient of the Radcliffe Fellowship from Harvard University, Friedrich Wilhelm Bessel from Humboldt Foundation 2015, and a graduate fellowship from the Japanese Ministry of Education and Science from ACS. So in Professor NAUMOV's groups in Abu Dhabi, the main topic is study of advanced materials, focusing on the development of smart materials, able to respond to self-repair, to self-clean, to sense for applications like robotics, organic, micro-optoelectronics, desalination technologies, and enhanced oil recovery in the petroleum industry, for example. So, Panche, if you can hear me, it's up to you, and thanks for your nice presentation.
Thank you, Sylvie. I hope you can hear me all, and thank you very much for the invitation. I think I'm going to switch my video at some point because I would like to have this transition fast. I just wanted to thank the organizers for inviting me to this conference. It's my first time presenting at the ICNI Symposium, and I really would like to be part of this community in the future as well. I was really happy to see this transitioning from some definitional issues at the beginning. So we went to see some beautiful organic chemistry and then some computational aspects of the non-covalent interactions. And now we are switching to coordination chemistry. And so I'm actually going to take you to the next level, which is crystals. I think my research is quite complementary to what has been shown here in this symposium. And I think the previous lecture was a quite good introduction to what I'm going to talk about. But I would like to show you also some of the applied aspects of the non-covalent interactions. And this is what our research is about, is basically we are trying to capitalize on the non-covalent interactions to induce some dynamic response from crystals. And I hope you will enjoy my lecture. So I'm just going to switch on the video now, and we're good to go. All right, so I would like to talk about the role of non-covalent interactions in eliciting dynamic behavior in molecular crystals. And I would like to start with saying that the chemistry is a science of change. This is the main motif in our research. And whether this maximum was demonstrated by the well-established world of molecular machines, switches, and rotors, it can really hardly be applied to static objects such as crystals. In fact, you might recall that the word crystal evokes images of translucent and hard and still solids which have regular faces. And this actually line of thought goes along with one of the most infamous interpretations of a crystal, such as the crystal being a chemical cemetery of molecules. And this perception was instigated quite a long time ago, with the very early days of the solid-state chemistry, and has been quoted many times in disapproval since then. And so now we are discovering that the crystals are actually not that still. There are dynamic aspects of the solids, and they have been the subject of a plethora of reports pertaining to the dynamics of molecules and crystals. Especially we've seen some of that in this conference so far, so the so-called amphidynamic crystals, molecular rotors, solid-to-solid phase transitions, especially those that have been extensively studied in the level of molecules, as well as the supramolecular assemblies. I'm just going to try to go on to the next slide. we're interested in something called actuators, and actuators are defined as materials, devices, or even complex biological systems that function as transducers of energy supplied by external source, and they are able to convert this energy into mechanical energy in a controlled manner. And so they share the same basic thermodynamic principles of energy transduction and are collectively referred to as actuators. So the current applications of actuators are really many and diverse. So they include sensors. You can think about artificial muscles, soft robotics, and energy harvesting materials. The motion in these actuators can be used by heat, light, electricity, pressure, sometimes even moisture and even chemical reagents, and even humidity, as I mentioned. And they can be realized with shape memory polymers, conductive fibers, some liquid crystal elastomers, piezoelectric, magnetostrictive, and even electromagnetic materials. The next topic that I would like to go on is the soft robotics. You probably know that the strength and toughness are mutually exclusive assets of a material. However, the nature has managed to combine these into biogenic architectures, which have extraordinary complexity. And these architectures actually continue to inspire man-made engineering and industrial designs. So while very complex natural biomechanical systems have evolved to aid some functions such as dispersal and survival, the artificially manufactured actuators are specifically designed for integration in mechanotronic or adaptronic systems. And these can range from miniature devices, for example, such as are used for navigation and positioning devices in flying machines, to rather complex systems that can perform tasks in specific environments. And these can be, for example, humanoid robots and spacecraft. And so the principle of biogenic actuation are harnessed to create soft robots from highly compliant materials, similar to those that are found in living organisms. And the soft robotics as a direction actually of research draws very heavily from the way in which living organisms move and adapt to their surroundings. So what we want to capitalize on is that crystals, organic crystals in particular, having mechanical properties that are somewhere in between natural organisms and conventional robotics. In this very complicated plot, you can actually see the Young's modulus versus density for organic crystals, which are co-plotted with those of other materials. And we did a systematic and exhaustive analysis of the basic mechanical properties of organic crystals, which are reported for the past 3 decades. And we tried to rationalize the exceptionally high stiffness and hardness of some of the organic crystals, which can actually compete with some of these materials that are used for soft robots. So these global materials property plots for molecular organic crystals actually highlight the high performance materials that fall into 2 distinct subsets of crystals. The first includes saccharides, such as sucrose, arabinose, and xylose, as well as some other similar organic crystals, for example, ascorbic acid, where neutral molecules that are endowed with proton donors and acceptors can make a conducive medium for more hydrogen bond formation. The location of molecular crystals in this global material space actually is in line with the generic claim that organic crystal represent, first of all, distinct materials class, and this class bridges the gap between rigid or dense materials, such as ceramics, metals, and some composites, and more compliant light materials, which are elastomers, polymers, and foams. In the same time, organic crystals conveniently overlap with the mechanical properties of some biogenic materials. So this specific combination of properties, which is first ordered crystalline lattice, and second pronounced softness, which is not found with other materials classes, this indicates the potential to harness with these materials the advantages of this long-range structural order, and while we have the flexibility comparable to that of some of the soft biological tissues. Now, soft crystal is an emerging concept in materials research, and it seems that combines 2 seemingly diametrically opposed ideas. The first concept is crystals, which, as I mentioned, are normally hard and structurally ordered entities. And on the other hand, we have the soft matter. And this term usually refers to disordered materials such as polymers, colloids, liquid crystals, and gels. Since the early days of structural elucidation of soft crystals, this contrast between the structure and physical properties these materials has drawn the attention of researchers toward understanding their mechanically compliant nature and its relation to the long-range structural order. So now properties such as elasticity, superelasticity, and perelasticity, which traditionally have been related to inorganic materials, and even some phenomena such as shape memory and self-healing effects, and I will show more of that later in my presentation, that were originally established for soft materials, they are increasingly reported for molecular crystals. So the dynamic nature is obvious, but the mechanism, the quantification, and the relation to the crystal structure in organic crystals are not immediately intelligible to the chemistry and material science research community. So without intending to overwhelm you with many formulas, I would just like to show you quite a few examples now that have been reported of these dynamic crystals. So here, for example, you can see crystals that can be deformed by light, some that can be moved by light, and some that can be moved by other stimuli. And this is something that was reviewed in 2015. Obviously, there are many more examples that have been reported in the meantime. This is something that we have actually collected from the literature, but now we come to other groups actually being involved, and this community is rapidly growing. This is, for example, a summary from one of my colleagues that kind of summarizes the elastically bendable crystals. And as you can see, we already have quite a few compounds, and the number of these materials is continuously growing. And this is another review from another colleague from the US, where she collected all the examples of thermoelastic, superelastic, and ferroelastic crystals. And these are increasingly important because some of them, most of them actually, are completely organic, which means that they are very soft and at the same time they are very light. So we kind of overcome the main problem that we have with metals, which is their large density, and that translates into a large or heavy weight. So this now field is shaping into a new field in material science research, which bridges crystal engineering, solid state chemistry, and also some other fields. And it's called crystal adaptronics. So mechanically reconfigurable molecular crystals are shaping up a new research direction in material science, which we called crystal adaptronics. This is an emergent material science discipline, and it is intersection of the solid state chemistry and it explores the dynamic nature of mechanically reconfigurable, motile, or explosive crystals. Adaptive molecular crystals basically bring to the material science a qualitatively new set of properties that associate the long-range structural order with softness and mechanical compliance. So as you can see in this figure, in traditional adaptronic concept, you have a sensor, control unit, and actuator. In case of a crystal, you basically have all these three components into the same material. So the crystal, dynamic crystal, can be considered actually a new type of smart material. These mechanical effects that crystals can undergo are quite many. And regardless of how they have been induced, whether this has been by action with heat, light, or force, or even sometimes electric or magnetic field, as I mentioned, humidity, chemical agents, they, on a macroscopic scale, they can be classified as the deformation, motion, or disintegration. And these effects, or sometimes a combination of these effects, can be also categorized according to the outcome. So they can be categorized as restorative when we have preservation of crystal integrity, or sometimes can we have disintegrative effects where the portions of the crystal separate from the crystal. And in such case, we have a breaking or explosion. So the classification has direct implication for the target applications and is also device specific. So depending on the deformation, we can have an application to different devices. For example, the restorative effects could be applied to devices which are based on cyclic operation. While if you have a disintegrative effects, they are more appropriate for single event operations. So whether a disintegration will occur depends on multiple factors, obviously, which include the susceptibility of the structure to stress and the rate of accumulation of various defects during the process. In general, the retention of integrity depends on the interplay between the time for the accumulation of elastic and the time for this dissipation. And I would say also depends on the non-covalent interactions, which is why I'm presenting this at this meeting. So this combination of factors results in a large span of time of response of dynamic crystals, as you can see from this plot here. Our specific research interest in the past 10 years or so has been focusing on the so-called Salient crystals. These are quite interesting and quite rare crystals because they are capable of very fast transduction of energy. So unusually rapid and efficient energy transduction can be accomplished with these crystals, which are divided into thermosalient, photosalient, and mechanosalient crystals. These are three subclasses of dynamic materials which undergo cooperative martensitic transitions, and this results in rapidly release of elastic energy and is manifested as motion across distances, and these distances can vary from several millimeters to a couple of meters. It has been also demonstrated that the phase transition that underlie these kind of thermosalient crystals are exceedingly fast, and they're actually much faster than the other more common solid-solid transitions. So if we combine this property together with the easily detectable and measurable crystal expansion or contraction on a macroscopic scale, this asset makes distinct property for the thermosalient solids and favors these molecular crystals as controllable, work-generating elements that could be implemented as active part of actuating systems or devices. Important aspect is the temperatures of the thermosalient transitions. So in the past several years, over 20 new examples have been reported in the past decade, and these have been categorized in 3 different classes based on their structures, and we have a number of notable reports of serendipitous observations increasing in the past several years. So basically, the thermosalient crystals, as you can see here, can undergo transition both below and above room temperature. And they are a newly researched class of adaptive crystalline solids that are thought to be candidates for active actuating elements in organic micromachines. So micromachine made only from organic material. Together with these analogous phenomena, such as the photosalient crystals that can be triggered by light or by mechanical stimulation in mechanosalient crystals, they provide a new tool in the materials engineering toolbox. Aside of applications that require only one-time disintegrative events, which are exemplified with the metal-coated thermosalient crystals that were suggested, for example, to be used as solid fuses. I will tell you more about this later. Some of these thermosalient materials are sufficiently mechanically robust upon repeated phase switching to be even considered in devices for cyclic operation. An important aspect of this chemistry is the rate of this transition. So they are very, very fast. In fact, the thermosalient crystals are among the fastest switching materials reported to date because there is a concerted structural change associated with the martensitic phase transition, and this occurs 4 to 5 orders of magnitudes faster than some other non-cooperative transitions in the same or other materials. For example, in this case, we have 2 phase transitions, one thermosalient, the other one is not, and they're only about 10 Kelvin apart, and the propagation rate in the thermosalient phase transition is 5 orders of magnitude faster than that of the second non-thermosalient phase transition. Of specific interest are also transitions that can be induced by light, and we call them photosalient transitions, because in this case, you can actually control the disintegration of the crystal remotely, and you can have both time and spatial resolution. And so because of, in most cases, these salient effects are accompanied by a release of significant amount of elastic energy within a very short period of time, they result in ballistic events and oftentimes crystal disintegration. The disintegration usually starts by generation of cracks at defect sites, which act as actuators. So the future application of these kind of crystals is light actuators appear to be limited to single stroke actuation. However, multiple operation of these materials is in principle possible. However, the efficiency decreases in subsequent cycles. So in this case, for example, you can see you have basically a linkage isomerization complex, and we had to devise some sort of methods to be able to track the changes that occur with these materials. Moving along the photosalient transitions, we had to switch to thermosalient because in such case we have a better preservation of crystalline integrity. So the decrease of concentration of defects, if we try to grow good quality crystals, can be one viable approach toward improved cyclability of the actuators based on these transitions. An alternative strategy would be to use some of the so-called class 3 thermosalient solids. One of them is shown here, it's just a pyroglutamic acid. And in this case, this crystal includes extended hydrogen bonds networks in its structure. And so this subset of thermosalient materials is known to be much less prone to disintegration because there is a more effective dissipation of the elastic energy through these hydrogen bonded interactions. So if we miniaturize the thermosalient solids to micro or even to nanoscale, this could further contribute to preserve the crystal integrity. And if we combine this with hydrogen bonds and absence of significant defects, they could be considered for further improvement of the performance in a cyclic operation mode as opposed to single stroke operation. Now I would like to switch gears here to much slower dynamic processes, and in particular crystal deformation, where also the non-covalent interactions play the most important role. So just to give you kind of a one-on-one introduction to mechanical testing or deformation of crystals, well, if you go with the classical mechanical principles, whenever apply stress on a solid object, the object will initially undergo elastic or reversible deformation, and this is followed by plastic or irreversible deformation. And this goes on while until you induce a fracture, and then the crystal or object will break. So for small stresses, stress strain, for more stresses, basically, this stress strain curve, initially, as you can see from this plot, is linear, and this follows the Hooke's law. And you can estimate, not really determine, but estimate the elastic modulus of the material from this elastic regime as a measure of its stiffness. After the applied stress displaces the molecules in the crystal and the stress is removed, the intermolecular forces will restore the original positions and the material will recover the original shape and size. However, once the upper limit of the elastic regime is reached, the material will undergo permanent or plastic deformation. And if it's stressed beyond the plastic region, it will yield and the crack will occur. So based on the difference in shapes and the limits of the stress strain diagrams, the materials can be classified as brittle or ductile or elastic as plastic. And now this is really a hot topic in solid state research where we're trying to kind of estimate or predict the elasticity or brittleness of different crystals. Also, there are also a number of other phenomena that have been reported in the past, which are really quite surprising and also could be potentially useful. So as you might be aware, a typical elastic material does not go structural phase transformation until under applied force. In fact, the elastic materials show modest strain of only up to 2% for metals and only about 4% for molecular crystals. If you apply additional stress, this will result in fracture of the material. Now, there are recently reported superelastic materials, superelastic crystals, which, when subjected to external stress, face a partial loss of elastic energy due to a phase transition. It is something which is similar to the well-known shape memory alloys or the transition between austenite and martensite phases in steel. These kind of crystals can sustain strains of up to about 10 to 12%, and moderately deformed superelastic molecular crystals are able to recover their shape by undergoing martensitic or diffusionless transformation. This property, the superelasticity, can be attained either by phase transition or by twinning. Now, here on the right-hand side, you can also see ferroelastic crystals. So in contrary to the superelasticity, where the stress-induced deformation can be recovered by removal of the stress or by heating to the temperature of the reverse transformation, in case of ferroelasticity, this property is actually a stress-induced deformation, which is irreversible. So it is associated with a reorientation process where the deformation, which can be twin or polymorphic, can be reversed by applying a reverse stress of these materials. So there's a lot of excitement and also studies into these materials and also comparison of these properties. Another property which is important is simple plasticity. In fact, in many crystals, this elastic regime is so small that basically they can be considered as plastic materials. You can see here a material which is organic crystal, which can be simply mechanically deformed into arbitrary shape and size with the multiple kinks and also with multiple shapes. So these kind of properties are new and are very important because this provides us a basic mechanical characterization of the material, and in this case, the material being an organic crystal. So in this particular case, you see single crystals of hexachlorobenzene, and also there are some other materials as well, which can be bent mechanically at multiple locations to 360 degrees, and they retain the macroscopic integrity. And this extraordinary plasticity proceeds by segregation of the bent section into flexible layers. And this happens by obviously evolution of the dislocations of some defects. And the molecular layers slide on top of each other over these defects, and thereby they generate domains with slightly different lattice orientations. So we have done a lot of different analysis on these plastically bendable crystals, not only of this material, but also a number of other materials. And the combined microscopic, spectroscopic, and diffraction analysis of the bent crystal basically showed that this preservation of crystal integrity when stress is applied, in this particular case on 001 phase, this requires sliding of layers by breaking of and reformation of halogen-halogen interactions or bonds. And this is where, again, the non-covalent interactions come into the picture. If you apply stress on the 100 phase of the same material, and this is in the direction where the pi-pi interactions dominate the packing, this leads to immediate crystal disintegration. So you can see that anisotropy of the crystal plays a critical role in how the crystal responds to mechanical stress, which is very, very basic property, and we still do not understand it. So, but also this example kind of highlights the yet unrecognized extraordinary malleability of the molecular crystals, and also the critical effect of strongly anisotropic supramolecular interactions on the mechanical behavior. Now, with these kind of analysis or studies, you also have to have a specific methods to be able to understand how this all works. And in many cases, we had to devise or adapt experimental techniques to be able to look at these phenomena. So one of them is shown here. Because of the crystallinity of the bent crystal is lost as a result of accumulation defects. We have demonstrated in this work that spatially resolved microfocus infrared spectroscopy by using synchrotron radiation can be applied in conjunction with the periodic density functional theory calculations to predict the spectral changes or to extract information on structural changes that occur as a consequence of bending. And so this approach reproduces well some observed trends, such as the wall effects, and also provides estimations of the vibrational shifts, unit cell deformations, the intermolecular parameters, and so on. In general, we conclude that expansion of the lattice induces redshift, while compression induces larger blue shift of the characteristic modes. And since this approach does not include parameters related to the actual stimulus by which the deformation has been induced, one can use this approach basically to generalize it and to apply it to other mechanically, photochemically, or thermally bent crystals. A side result of this analysis was actually observation that organic crystals can decrease the melting point when they are bent. So as you all know, the melting of any pure crystalline material at constant pressure is one of the most fundamental properties, and it has been used to identify organic compounds or to verify their chemical or phase purity since the early times of chemistry. Both our group and also other groups have observed that with the plastically bent crystals, there is a small and yet significant decrease in the melting point of about 0.3 to 0.4 Kelvin. So the bent section of the crystal was found to be mechanically softer relative to the straight sections, and this softening temperature preceding the melting was also lower on the convex side of the bent crystal. So melting of the bent crystal starts at the kink of the crystal and often appears as a splitting of endothermic peaks in the TSC fingerprint, while unilateral compression of the crystal results in multiple peaks. So these thermomechanical effects become more pronounced with heavily damaged crystals due to obviously increased concentration of defects, and ultimately they result in a large temperature spread of the associated phase change, in addition to some melting point depression in the form of or damaged crystals relative to their pristine counterparts. The mechanical treatment during sample preparation has a profound effect on the melting of a pure substance, and this result could be critically important where you need to determine the exact melting point, for example, for purpose of structural identification, polymorph identification, or purity check. Another interesting property is the so-called shape memory effect. In 2016, we reported that upon bending, single crystals of terephthalic acid are able to undergo partial mechanically induced phase transition without delamination. And the overall crystal integrity is retained. So the minimal force required to induce the transition of the stable form to the metastable form by bending was found to be several tenths of millinewtons. Both phases coexist at the kink of the mechanically bent crystal. Such plastically bent crystal can act as bimorpho, and their phase uniformity can be recovered thermally by taking the crystal over the phase transition temperature. And this recovers the original straight shape, and the crystal can be bent by a reverse thermal treatment, and this results in shape memory effect, which is similar to those observed with some shape memory metals, as you can see here from the video, or alloys. And these alloys are actually used in medical devices. So somehow the crystal appears to retain the information of the deformation structure. And this transformation between bent and the straight shape of the crystal can be repeated several times by alternative heating and cooling, and we do not see any deterioration of the crystal. In fact, we were so interested to see what is happening that we use a microfocus X-ray to study these crystals. So the bent crystal of the form 2 terephthalic acid was analyzed by using microfocus XRT using synchrotron radiation, and refinement of the crystal structure at the 2 points of the crystal, so outer and inner point, confirmed that the two phases coexist in the bent crystal, and their structures are identical to those of the pure phases. So this result presents evidence that the inner part of the crystal has undergone phase transition during bending as a result of application of local pressure, and that the two phases of the crystal coexist in the bent crystal. We think that similar memory and restorative effects are more common of other molecular crystals having metastable polymers, and of course it would be nice if they are investigated further. Now, one of the issues in this research is how to quantify these effects, and there has been a lot of effort to do that because and we started with the so-called thermosalient crystals that I mentioned before. If we compare with the actuators that have similar work capacity, thermosalient crystals are very much lighter, so they are 2 to 10 times lighter. And so this low density, which translates normally into a lightweight, together with the ordered structure of these materials, the significant strength and the competitive work capacity, these are the greatest advantages to be considered in the future applications of these materials. So we attempted to use a direct measurement of the actuation force generated by this crystal of a thermosalient solid, and we attempted to quantify the work performed and the energy conversion that can be accomplished by using dynamic crystals as supramolecular actuators. In these measurements, we use small crystals, usually sub-millimeter to millimeter size of one organometallic compound. You can see the structure here. And they were found to exert forces which range between 1 and 100 millimeters upon expansion. If you calculate and translate this into density, power density, this comes to a volumetric power density of about 1 to 3 megawatts per cubic meter, and this is kind of sufficient efficiency comparable to the existing multi-component and component actuators. Further on, we can actually make plots which represent this kind of performance and compare it more directly with other materials. So, for example, in this plot, you can see the values which are co-plotted, values from the previous experiment that I mentioned, which are co-plotted against respective values for other actuators. You can see that the volumetric power density of the PHA crystals exceeds the values for some common materials, such as moving coils and some shape member actuators with comparable strain values. Also, in comparison with the thermal expansion actuators, the strains that can reach with this small crystal are an order of magnitude higher without a significant toll on the volume power density. You can also conclude that based on the temperature difference between the two forms, these crystals can be classified as thermal expansion actuators. So much higher strain values with similar volume power density can be obtained from these crystals with only 50 Kelvin temperature rise relative to the existing thermal expansion actuators, which normally require a temperature rise of about 100 Kelvin. Moreover, these crystals can be cycled several times simply by heating and cooling and without the requirement of a mechanically coupled system to reset the original state, which is a very important limitation with the currently used shape memory and solenoid-based actuators. So the thermosilent crystals also can provide the added benefit of being lightweight actuators because their density is significantly lower than that of the conventional shape memory and bimetal-based thermal expansion actuator. This is another example that I would like to show, a very simple compound, which is a hexamethyl benzene, a very old compound whose crystal structure was determined back in 1928 by Catherine Lonsdale. And this is interesting compound because it also undergoes a very fast phase transition. It is capable of rapid and complete structure switching, and it undergoes a martensitic phase transition. This transition has a tremendous potential as thermally driven organic actuator. So in this case, we demonstrated that the work can be performed by this crystal is comparable to that of the most actuator classes. So millimeter size crystals of this material can undergo transition between two forms by uniaxial expansion, and they exert force of about 10 to 100 millinewtons. If you compare the force to weight ratio of the crystals, it is 10 to the 4 times, so 4 orders of magnitude better than that some of the living creatures, for example, horses, elephants, and ants. So an actuator performance chart of this compound reveals that the performance of this material is close to that of the nanomuscles, electrostatic actuators, and voice coils, with a very high strain, higher strain than electro and magnetostrictive actuators, and even ceramic piezoelectrics, and stresses that are higher than that of the electroactive polymers, MEMS devices, nanomuscles, voice coils, and some other solenoids. Moreover, the crystals of these materials are mechanically compliant and can be bent reversibly and shaped to fit into the desired application, which is not always possible with other materials. So our intention is to establish this kind of global performance indices to be able to assess how good these crystals are. In fact, systematic study on a larger data set and using selected performance indices that are common in the materials engineering practice is really required at this point to be able to realistically assess and thoroughly assess their performance. So we went on further to set general performance metrics that can be used for quantification of the performance of these prospective dynamic materials. The indices were calculated on two selected representatives of thermosilent solids, which are shown here. One of them is pyroglutamic acid, the other one is a co-crystal between two molecules. The indices showed that by direct measurement of the attributes for a single component crystal and crystal, we were able to determine the range of forces which they can exert and the work that they can perform. And so then we use these parameters to establish a performance window for this distinct class of engineered materials within the global actuator materials property space. And then by comparing these values with extensive database of actuation, we attempted to identify the relevant parameters and to systematically compare the performance of these two solids with other common actuator classes. For example, we found that they are the lightest of the available thermal actuators, and they currently are also the only lightweight actuators with a single component of uniform composition and ordered long-range structure. However, due to their small size, which is inevitable due to limitations with crystallization, they generate a small maximum forces than most of the known actuators. This results in relatively small actuating stresses at intermediate values of the actuating strain. However, it is important to note here that the thermosalient crystals undergo large changes in size, and this is reflected in high strain of these materials. In fact, the strain exerted by these materials is comparable to those of other thermal actuators, shape memory, alloys, polymer gels, solenoids, and also some hybrid actuators, which is, for example, piezoelectrics, electrostrictors, and magnetostrictors. So along the same lines, I would like to mention that due to the small size, thermosalient crystals are able to produce very small amounts of work. This is what we actually know, how much work we can get with these materials. However, the work increases by increasing the crystal size. So they have a higher work capacity than electroactive polymers and some MEMS-based devices, and they perform close to piezoelectric transducers, voice coils, and some ceramic piezoelectrics.
1 minute.
1 minute, okay. Okay, altogether the results indicate that if the challenge with fabrication and implementation in devices are overcome, adaptive molecular crystals can have far-reaching implications for emerging fields such as electronics and soft microrobotics. So I'm going to skip the rest of my talk and go to the end. I wanted to show you some of the applications and perhaps how we can determine these performance indices, but I would like to keep to the time. So I'm going to just show you some of the self-healing polymers that we used as an inspiration to create self-healing crystals. And of course, we did made the self-healing crystals based on disulfide shuffling. They are shown here. We achieved 7.8% self-healing in these disulfide-based crystals, but then by using other chemistry, we improve this efficiency. So here, for example, you can use you can see self-healed crystals, which can be mechanically disturbed without actually without losing the integrity. And also we use the computer tomography to look inside these crystals and look at their integrity and see whether the self-healing has occurred. Now we have improved this self-healing from about 7% to 67% by using a boronate chemistry. And basically, we can also do multiple cycles of self-healing. The self-healing decreases down to 44% after 5th cycle. Okay, I'm just going to perhaps show the basic concept. And this is basically we want to use light, heat, or force, applies these on the crystal and use the crystal as a dynamic entity to produce some sort of force. And recently, we're kind of expanding these to also be able to produce the crystal. But if you would like to think about in a more holistic way, the general concept here is using dynamic materials, and in our cases, organic crystals specifically, to be able to convert among different types of energy, in particular mechanical, radiation, kinetic, and thermal energy. So sorry for going a little bit over the time. I would just like to invite you to a conference that I'm organizing next year here in Macedonia. It's if you're interested in non-covalent interactions and organic crystals, you're welcome to join us between July 3rd and 8th. We will have a fantastic line of speakers, and all of you are welcome to come and join. And finally, I would like to thank my group, which basically we have a very diverse group of people. They come from all over the world. They are very enthusiastic. I'm very happy to be able to work with them. And of course, to thank our sponsors and to invite you to visit some of our social media presence and learn more about research. And I would, again, thank you for your invitation, and we'll be happy to answer any question.
Okay, thank you, Panche, for this nice travel into the world of crystals. That was really interesting to have properties.